Welcome. We have been discussing about basic iterative methods, namely Jacobi iterations and Gauss-Seidel iterations. In last class, we tried to discuss about the base algorithms for these basic iterative methods and also tried to give an idea about what is convergence of the iterative methods, or when should we say that the iterations have converged to the exact solution or near exact solution, with the difference being a very small number, which is kind of the machine precision of the particular computer is of that order, and we will say that the solution have converged to that solution. So, we will start with a guess value and follow the iteration steps, and at the end we will get a converged solution, which is the practically the exact solution of the equations. So, these methods we have discussed in the last class, and we will look into more detail of these two methods, Jacobi and Gauss-Seidel iterative methods, in this class and also in the subsequent class, and we will try to have better insight on the convergence of these methods, what are the requirements for these methods, and as well as what are the methods to improve convergence, so that we can get the converged solution in less number of iterations in less time and also doing less computational work. So, we will start looking into the both this method, Jacobi and Gauss-Seidel methods. So, first let us look how should this method look like when we represent them in the matrix form. So, we are discussing about Jacobi iterative methods first, and then we will look into it the matrix form, because last class we have only looked into the equations individually and looked it as a collection of equations, not as a matrix equation. So, now we will start looking into it as a matrix equation. So, we are solving the matrix equation A x is equal to b. Now, if we see in Jacobi, in each step what we are doing is basically we are starting with a guess value and we are updating the guess value based on the iteration. So, the updated value may be x k plus 1. So, this is the fallout of first iteration. We start with first iteration with the guess value x 0 and the updated value is x 1. So, this is for the ith term, and for the term for ith equation we will only update the ith component of the x vector or ith x, which is aii, which is the diagonal term x I k at k plus 1th level. Then this is the ith equation in the kth iteration, or rather k plus 1th iteration. Ith, we are looking into the ith equation. So, this will be sum of a I j x j at kth level and I less than j. So, except I is equal to j, all the terms will be considered as at their previous value or at the guess value I j x j k, and here I is greater than j is equal to b I, right. So, this is what are the form of Jacobi iteration we have given in the last class. So, this a I now if we look into these terms, this is the diagonal term, this a I j x j k where I is less than j. I is less than j means they are the subdiagonal terms or the lower triangular part terms. So, this is below diagonal and this is above the diagonal of the matrix. So, A matrix can be composed into three components. One is the diagonal, another part is a lower triangular form, which is the below diagonal part, another part is the upper triangular part, which is the above diagonal part, and x vector and the updated x vector are multiplied with these three matrices. For Jacobi, the x vector is multiplied, the guess x vector is multiplied with only the below and above diagonal term, and updated vector will be from the diagonal term, and in Gauss-Seidel the updated vector is multiplied with diagonal and below diagonal term, and the guess will be updated with the above diagonal term. So, we can look into the, we can say that the matrix A x is equal to b, for matrix equation A can be split into three components. One is the diagonal component d, another is the lower triangular component minus E, another is the upper triangular component minus F. And now, we can write the Jacobi step as x I k plus 1, which is the updated x vector. From here I can directly write it is b I minus j is not equal to I a I j x j at kth level by a I, which will mean that b I minus the terms of x vector, which will be multiplied with the lower diagonal part. So, this is basically this part is basically my E. Instead of minus E, I am writing it E because I have taken it into the right hand side, and this part is F. So, this is E x and this is F x, and this x is at kth level. So, we can write as the matrix equation d x at k plus 1 minus E x, which is at the guess level kth level, minus f x k is equal to b. This is the matrix form of this equation, and we can club them and write that d x k plus 1 is equal to b plus E plus f x k, or x k plus 1 can be obtained as d inverse b plus d inverse E plus f x k. So, though this is a matrix equation and we are getting inverse of the matrix, because this d is a diagonal matrix, d inverse is getting d inverse is nothing but dividing it by the term 1 by a I I. So, d inverse is basically a matrix where all the inverse of all the diagonals are present in that matrix, and this is trivial to find out d inverse. So, this step is not basically a matrix inversion step, rather a simple algebraic step, one operation algebraic step to find out x k plus 1. So, nevertheless, this is the matrix representation of a Jacobi step. This is the matrix representation of a Jacobi step. This in same light, we can also represent a Gauss-Seidel step. So, let us look into a Gauss-Seidel step. The Gauss-Seidel equation will be that updated vector will be multiplied with the lower diagonal term also. So, this is E x k plus 1, and with the upper only with the upper diagonal the guess vector is multiplied. So, this is f x k. So, we can write the Gauss-Seidel matrix form as d x k plus 1 minus E x k plus 1 minus f x k is equal to b, which is d minus E x k plus 1 plus is equal to b plus f x k, and x k plus 1 is d minus E inverse b minus d minus E inverse f x k. Again, if we look into matrix form, this is inverting a lower triangular matrix, because this d plus E minus E, or this part gives me a lower triangular matrix L. So, inverting a lower triangular matrix is also not very difficult, and that is how we can get this step done easily also. So, both Gauss-Seidel and Jacobi can be formed as a matrix equation in which x k plus 1 or the updated x vector comes out as some inverse multiplied with another matrix into x k plus some inverse multiplied with the v vector. So, we will try to look into the general form, and this is important because the properties of these iterative steps, which will determine how fast will they converge or what are the restrictions on their convergence, will come through looking into these matrices. This is related with the properties of this matrix, because now we can see that this is right now is a matrix inversion problem. for example, d earlier we got d inverse e plus f x k. So, if d in the Jacobi method we got the step to be x, in the Jacobi method we got the step to be x k plus 1 is equal to d inverse b plus d inverse e plus f x k, and the requirement for this is that d inverse cannot be a singular matrix. So, D must have all non-zero vectors here. Similarly, a requirement for Jacobi. So, this is an apparent requirement. We will look into the requirements in much more detail in next few after next few slides. Here the requirement is that D minus E inverse has to exist. So, D minus E cannot be a singular matrix. So, diagonal minus the lower triangular cannot also be a singular matrix. So, all these requirements for the case matrices for which we can get solution through these iterative methods will come out as this analysis. So, it is important that we should look into these iterative steps in their matrix form. So, nevertheless, both these forms like the Jacobi form and the Gauss-Seidel form, both this form has something similar, and similarity is that in appearance they look similar. The updated vector is some vector which contains some inverse multiplied inverse of a matrix multiplied with the solution right hand side vector b plus inverse of some matrix multiplied with another matrix maybe into which is multiplied with the guess value x. So, this is a general form of this matrices. It is like x k plus 1 is equal to say f plus m inverse n x k or something like that. So, let us look into the general form. The general form of an iteration step both Jacobi and Gauss-Seidel is m x k plus 1 is equal to n x k plus b, where n is m minus a. So, a component of one component of a is subtracted from a and this comes as m, or whatever is in m the remaining is m minus a. If we sum at the converge state, when if it converges to one particular solution. So, m x is equal to m minus a x b, which is a x is equal to b. And if we think, if we recollect, a is equal to d minus e minus f, diagonal minus lower triangular, right, diagonal minus the lower triangular minus of lower triangular. So, diagonal, lower triangular and upper triangular part, and in Jacobi it is d x k plus 1 is equal to e plus f x k plus b, and in Gauss-Seidel this is d plus e x k plus 1 is equal to f x k plus b. So, we can see that if we add, if this is m and this is n, similarly here this is m and this is n, if we add m and n, this should give me a. So, we can write that for Jacobi m is equal to d, n is equal to minus e minus f. For Gauss-Seidel m is equal to d minus e, it is not d plus e, rather it is d minus e, because this is d. This is d minus e, just a second, and this should be minus n, rather this should be minus n. So, n minus n is equal to minus e minus f, and minus n is equal to e plus f, and minus n is equal to f here. So, this is minus n. So, nevertheless, so both these can be expressed as a general form, which is m x k plus 1 is equal to minus n x k plus b. So, now if we further look into these steps, that m x k plus 1 is equal to m minus a x k plus b is a general form of any iteration step in Gauss-Seidel or Jacobi. So, you can write m x k plus 1 is m minus a x k plus b, x k plus 1 therefore, will be m inverse m minus a x k plus m inverse b, and this is written as a general form x k plus 1 is equal to g x k plus f. So, this becomes my so this will become g and this is f now, and this g is called the iteration matrix. So, I will write this is equal to g and this is equal to f. This g is called the iteration matrix. With this g we multiplied our guess value matrix with this g and add with an f and get the updated value. And finally, this g is something which is being multiplied with the guess value and then we are shifting it also. The subsequent multiplication with g and shifting by f should finally take me to the converse solution. That is the idea of any iteration step. So, when the iteration will converge, we will get. So, when the iteration will converge, it will practically converge to one particular value, and we will see later that it asymptotically converges to this value. At the converge step, x k plus 1 and x k does not have much difference, they are essentially same. So, and we can put it into the equation also in the converge step. The converge step, as it will satisfy b minus a x k is equal to a x k plus 1 is equal to 0, we will see x k plus 1 and x k are being essentially similar. So, we get a converge solution where x cannot be further updated, x has converged to a particular solution, and the equation then x k plus 1 when the iteration will converge will get x k plus 1 is nearly equal to x k at convergence. So, if we will look into x k plus 1 is equal to g x k plus k, both will be both will have same value x, and we will get a equation x is equal to g x plus f at the limiting step. Therefore, x is equal to I minus g inverse of f. Now, if we look into this particular equation x is equal to I minus g inverse of f, this is the solution, this x is the solution of the equation. So, this x should also satisfy a x is equal to b. Then when the equation satisfies x is equal to b, x has converged to the right solution. So, x is we can get the converge step x is equal to g x plus f or x is equal to I minus g inverse of f. So, x is equal to I minus g inverse of f must be this x must be a solution of x is equal to I minus g x is equal to b, this two x's should be same. So, they must be coming from the same solution. So, let us see what is I minus g inverse. G is equal to, we know that g is equal to m inverse m minus a, which is nothing but I minus m inverse a. So, I minus g is equal to m inverse a. Therefore, I minus g inverse is equal to m inverse a inverse, which is the order will change a into a inverse multiplied by m. Similarly, f is equal to m inverse b. So, that should imply that I minus g inverse f, which is x is equal to a inverse m into m inverse b, this is a inverse f, which is a inverse b. So, this is same as x is equal to a inverse So, essentially through the iterations we are finding out x is equal to A inverse b, we are solving the right equation only. However, we are doing iteration because we are not doing a direct solution like Gauss-Seidel or LU decomposition, which essentially inverses the A matrix. Why aren't we doing this? We are not doing this because we have seen Gauss-Seidel is extremely expensive. It takes, if there is a 3 by 3 matrix, it should take 3 to cube or order of 27 operations, and if this is a very big matrix, the number of operations will be large, therefore, computing time will be very high, the perturbation due to round of errors will be very high, etc. So, we are not doing direct inversion, we are doing an iterative method which is same as inverting another matrix I minus G inverse. So, I minus G must be invertible here. Instead of solving A inverse, we are finding I minus G inverse. I minus G must be having some properties for which the I minus G inversion should be simpler, or iteratively what the iteration steps will do will basically find out an I minus G inverse. So, you remember that this G is independent of x k, G only has certain components of A, the decomposition of A and multiplication among these decomposed components or their inverses. Now, this what we are doing, we are not solving A inverse, we are trying to find I minus G inverse. So, it is important that along with A, I minus G or the G matrix should have some properties for which it is simple to, or it is easy to invert I minus G inverse. Also the issues like condition number, etc., along with A, now we have to look into I minus G also. So, that it is less perturbed by the numerical errors. Inverting different matrices needs different efforts. For example, if we have a full matrix of n into n order, inverting is something like doing a Gauss-Jordan step over the matrix, which will take n cube operations. But if we have a diagonal matrix, it will take less operations. If we have a triangular matrix, it will take little more operations, but not as many as the fully densed packed matrix. So, inversion also depends on the nature of the matrix, and we have to see that how easy is to invert I minus G inverse, and we will also see that if I minus G is a singular matrix, we cannot invert it. So, we will also need to see in which cases we can invert I minus G, and what exactly happened to A or to the equation system in case G becomes a singular matrix, what happens to the iterations. Because we are not directly inverting it, we are going through certain steps. Since G becomes a singular matrix or G is very close to a I minus G becomes a singular matrix or G becomes very close to an identity matrix, what happens there? We will look into these cases also. So, we now have to concentrate on G matrix. In next few slides we will do that and see how this I minus G inverse happens and what is its implication when we think of inverting this through an iterative method. So, one direct fallout of this formulation is that this has a solution if I minus G is non-singular. So, G cannot be an identity matrix, I minus G must be a non-singular matrix. Okay. So, we further look into these things. Let us say that a general form of an iteration step what we got x k plus 1 is equal to g x k plus f. Let x star be the actual solution. So, a x star is equal to b, and we have seen that this will give us m x star is equal to m minus a x star plus f, which is x star is equal to g x star plus f. What we are doing last slide, that if x when we have exact solution, this is equivalent to writing x is equal to b in a decomposed way, we will get x is equal to g x plus f or x star is equal to g x star plus f. So, the final step will be x star is equal to g x star plus f, final iteration step, because it has converged to the actual solution. The iteration step before that, say some steps before that, we have a k plus 1th iteration step, which will be x k plus 1 is equal to g x k plus f, which is the general form of the iteration step. What is happening in final step? x k, it has k plus 1 and k both converge to the final solution. So, you can write x star, we can write x star instead of that. So, if we subtract these two, we can see what is the difference between a updated solution and the actual solution, and we call that error during any iteration is x k plus 1 minus x star, which is g of x k minus x star. So, the error or the difference from the actual solution and the guess solution is multiplied by g times when we are coming to the updated solution. So, this multiplication must reduce the error, and that then only we can approach to the convergence of the solution. Or if we write the series x k minus x 1 x 0 minus x star, x 1 minus x star, x 2 minus x star, and go on up to x k minus x star, this must be a monotonically decreasing series. So, that we can get a converse solution. So, let us go to the next slides. So, let us call this our relation 1. Again the convergence step is x star is equal to g x star plus f. The kth iteration step will be x k is g x k minus 1 plus f. Subtracting, we get x k minus x star is equal to g x k minus 1 minus x star, which is the relation 2. And now using 1 and 2, we can write x k minus x star is equal to g of x k minus x star, what we got earlier, and we have also seen that if we carry on this relation, we have seen that x k minus x star is g of x k minus 1 minus x star. So, this will be g square x k minus 1 minus x star. Similarly, we can, if we further write like x k minus 1 iterative step is j x k minus 2 plus f. So, if we subtract them, we will get x k minus 1 minus x star is equal to g into x k minus 2 minus x star. So, here we can further substitute this and we will get g cube g square x k minus 1, we will get this as g cube x k minus 2 minus x star, and we can go on and still get finally get g to the power k plus 1 x 0 minus x star. So, what is the initial gate x 0 and the after kth iteration the guess k plus 1th iteration guess k plus 1, they are related as the difference from the actual solution x k plus 1 minus x star is g to the power k plus 1 x 0 minus x star. So, this the initial error is being multiplied by k plus 1th time after k plus 1th iteration, is being multiplied by k plus 1th power of g. So, every time I am multiplying the error by a g, and finally, the initial error will be multiplied by g to the power k plus 1 to get x to the power k plus 1 x k plus 1 minus x star. So, if g is a small value or if g is less than 1, then we will do several multiplication and finally get a converse solution. So, x star is the converse solution and x 0 is an initial arbitrary initial guess if it happens. We can write g x k plus 1 minus x star is g x k plus 1 x 0 minus x star. So, at k plus 1 iteration step, the solution converges to the final value x star for any x 0, any guess x 0. If this difference is very small, we will say that this has converged if convergence at x k plus 1th step will tell me that the difference x k plus 1 minus x star is less than epsilon, epsilon is a very small number. So, this will converge to this will start for any x 0, this will start with a finite value and go to a very small value if the norm matrix norm of g to the power k plus 1 goes to 0, then this difference, if this norm goes to 0, then this norm will also be, this the different norm of the vector will also go to 0, and this is possible if G has a matrix norm less than 1, because any number less than 1 we multiply it several times, it reduces to further smaller number. So, if the iteration matrix G has a matrix norm less than 1, the iteration steps will converge to the accurate solution of A x is equal to B. We can get the right solution of A x is equal to B through a iterative method if the iteration matrix G has a matrix norm less than 1. Now, we will in next session we will further check that what happens to x k plus 1 minus x k, because we are telling that x k plus 1 and x k will be practically same at the convergence step. How under which condition this happens, and what are the implication of this condition, that modulus of matrix norm of G is less than 1, how does it important while we look into the property of the matrix A, or what should be the properties of the matrix A for which we should get modulus of G less than 1. We will look into it next classes, and also discuss how does it being implemented by Jacobi and Gauss-Seidel, what is the exact value form of G, and what are the exact matrix norm of G matrix in for different matrices if we think of Jacobi and Gauss-Seidel. We will look into next few classes. Thank you.